In the previous lecture, we discussed how Coulomb derived the expression for electrostatic forces between two charged bodies, and he found out that the force was proportional to the product of the two charges and was inversely proportional to the square of distance between them, and the constant of proportionality was k, which he found experimentally to be 8.99 into 10 raised to 9. Now you must remember that Coulomb found this out way before we knew that electrons and protons were fundamental charge carriers, or even before we knew the structure of atoms and of the existence of electrons and protons. And so this was a significant achievement in the field of electrostatics, and in recognition of this achievement, the unit of charge is named after Coulomb, and so you have unit of charge, the SI unit of charge is denoted as 1C, which means 1 Coulomb. Now let's get an idea of how big a charge 1 Coulomb is. And so say if I have two charges of 1 Coulomb each separated by a distance of 1 meter, so these are my charges Q1, Q2 of 1 Coulomb, and let me find out what is the electrostatic force that charge 1 exerts on charge 2. Now obviously, since they both are positive charges, the force will be a repelling force, and so I can just find out the magnitude of the force, and the magnitude of the force is 8.99 into 10 raised to 9, that's my k, into 1 Q1 Q2 over r square, and that is 8.99 into 10 raised to 9 Newton. Now to get a qualitative understanding of how big Fe is, let me find out what will be the mass whose weight is equal to 8.99 into 10 raised to 9 Newton. And if I solve that for G is 9.8, I get M as 91.7 into 10 raised to 7 kilograms, and that's huge. What that means is that if I have a mass of 91.7 into 10 raised to 7 kilogram, the weight it exerts, the force, is equal to the force that two charges of 1 Coulomb separated by 1 meter will exert on each other. And as you can see, that is a huge amount of force. So why don't we feel a lot of electrostatic force in our daily life? We feel gravity, but we rarely feel being pulled by electrostatic forces. And there are two reasons for this. One fundamental reason is that we must remember that electrostatic forces act only on charged bodies. That means that if an object is electrically neutral, that means it does not have a net positive or a net negative charge, it will not experience any electrostatic force. So if I bring a neutral object, no matter how close I bring it to 1 Coulomb, and this object is neutral, there will be no electrostatic force. And that follows, another way to think about it is that if there is Q2 is 0, then this whole expression becomes 0 and there is no electrostatic force. And the second reason is that charges of 1 Coulomb rarely appear. 1 Coulomb charge is huge. You rarely see a charge as huge as 1 Coulomb. Usually you deal in microcoulombs, millicoulombs or nanocoulombs. And to get an idea of how huge 1 Coulomb is, we should note that lightning has a total charge of around 15 coulombs, and we know that lightning has huge charge, and if you say that the whole charge is 1 Coulomb, you can get an idea of how huge a charge 1 Coulomb is. Alright, so let's see in a simple example how we can apply Coulomb's law, and I have this simple example, and I want to illustrate how Coulomb's law can be used when there is a system of charges in place. So I have three charges, Q1 5 microcoulombs, Q2 minus 2 microcoulombs, and Q3 5 microcoulombs, and I want to find out the resultant force on Q3. What is the resultant force on Q3 due to Q1 and Q2? Okay, so let me begin. First, what I can find out very easily by Coulomb's law is I can find out the force exerted on Q3 by Q1, because Coulomb's law gives us the force between any two charges. So I can find out the force exerted by Q1 on Q3, and I can find out the force exerted by Q2 on Q3. And let me maybe use a nicer colored pen. So I will say, okay, so I will say I can find out F13 from Coulomb's law, and I can find out F23. Now, how do I find out? How does that lead me to the total force on 3? Now, if you remember, F13 is going to act at this point, and F23 is also going to act at this point, and so there are two forces acting at a point. Obviously, vector addition of those two forces will give me the resultant force at that point. So let's begin. So I will find out F13 as K, which is 8.99 into 10 raised to 9. Q1, 5 microcoulombs. I'll write it as 5 into 10 raised to minus 6. Remember this 10 raised to minus 6, do not forget that. 5 into 10 raised to minus 6 is my Q3, and R square, let me say my A is 0.1 meter, right? And R square is basically square root of 2 into 0.1 squared. And that essentially comes down to one important thing is, what is I'm writing the vector equation. So what is my unit vector? My unit vector is R13 cap, and that is the unit vector that acts from 1 to 3. So my unit vector is R13 cap, and if I solve this, I get F13 has magnitude 11 Newton. The unit vector is R13 hat, and so this is my answer. This is the force exerted by Q1 and Q3. It is in the direction of R13, and so I will draw it like this, and this is my F13. Okay, now what is the force exerted by 2 on 3? That is 8.99 into 10 raised to 9 minus 2 microcoulombs. So it is minus 2 into 10 raised to minus 6. Q3 is 5 into 10 raised to minus 6 over 0.1 squared, and that comes out to minus 9 R23 hat Newton. Of course, the unit vector here was R23 hat. Now R23 hat is defined as a unit vector that acts from 2 to 3. I can write this essentially as a vector of magnitude 9 and in the direction opposite to R23 hat. So that will be, this will be my F23. And that follows what we know. Since this is a positive charge, this is a negative charge, the force should be attractive force. Now it comes down to vector algebra. The resultant force on F3 is the vector addition of F23 plus F13. There are two ways to do that. You can either complete this parallelogram, you can draw these to scale, complete the parallelogram, find the resultant, or as we'll do now, componentize. And so we will take our axis parallel to 3 and the y-axis perpendicular to F23, and I will componentize F13 along a direction parallel to F23 and perpendicular. Let me see what my angle theta is. My theta is this theta, and since this side is A, this side is A, it is a right angle triangle. I can say my theta as 45 degrees. Okay, so let me write what F23 is. F23 can be written as a vector of magnitude 9 in the minus I direction, plus F13 can be written as 11 cos theta in I direction plus 11 sine theta in the j direction. And if I solve that, my answer comes down to minus 1.2 I cap plus 7.8 j cap. And this is the resultant force that Q3 experiences due to charges Q1 and Q2.